These examples go with section 5.5, trigonometric equations. This is part 2. Example 7. Solve the equation on the interval from 0 to 2 pi. The cotangent of x times the cosine squared of x is equal to the cotangent of x. All right, let's start this one off by subtracting that cotangent of x to the other side of the equation. What this is going to do is it's going to have my equation equal to 0. Then we're going to have the cotangent of x times the cosine squared of x minus the cotangent of x, because these are not like terms, and this is equal to 0. Okay, let's factor out the greatest common factor. That's going to be cotangent of x. This becomes cotangent x times cosine squared x minus 1 is equal to 0. That means the cotangent of x is going to be equal to 0, or the cosine squared of x minus 1 is going to be equal to 0. And if we add this 1 to the other side, we'll have the cosine squared of x equal to 1. All right, over here, if the cotangent of x is equal to 0, then we can say x is equal to the inverse cotangent of 0. And over here, if the cosine squared of x is equal to 1, we can say that the cosine of x, because we're going to square root it, and we don't want to forget the plus or minus over here because the square root was not part of the problem. So we have the cosine of x equal to positive or negative 1. All right, let's bring this up here. That means if the cosine of x is equal to positive 1, then x must be equal to the inverse cosine of positive 1, or if x is the cosine of x is equal to negative 1, then x must be equal to the inverse cosine of negative 1. All right. Back here, the angles where the cotangent is equal to 0. That means cosine divided by the sine. So essentially, we're looking for a place where the cosine is 0 and the sine is anything else except for 0. And that happens on the unit circle. It happens at pi over 2 and also at 3 pi over 2. Over here, the cosine is equal to positive 1. Well, that's just going to be at 0. And then the cosine is going to be equal to negative 1. This is going to happen at pi. Okay, now, we haven't come across this just yet, but now it's really important that we check our solutions and make sure they work in the original problem. Because what can happen is we can end up with solutions that give us something that is not defined. So we'll start with pi over 2. The cotangent of pi over 2 times the cosine squared of pi over 2 should be equal to the cotangent of pi over 2. All right, the cotangent of pi over 2, we already know that's 0. The cosine at pi over 2 is also 0, and we want to square that. And then 0 times 0 squared works. So pi over 2 is a solution. Now let's check 3 pi over 2. You'll see the cotangent. 3 pi over 2 times the cosine 3 pi over 2 should be equal to the cotangent 3 pi over 2. The cotangent of 3 pi over 2 is 0. The cosine at 3 pi over 2 is also 0, so this is going to be 0 squared. And once again, 0 times 0, 3 pi over 2 is also a solution. All right, let's check 0. The cotangent of 0 times the cosine squared of 0 should be equal to the cotangent of 0. The cotangent at 0, that's going to be 1 over 0, which is undefined. So 0 is not a solution to the problem. Let's check pi. The cotangent of pi times the cosine squared of pi is equal to the cotangent of pi. All right, at pi, the cotangent is -1 divided by 0. That is also undefined. Therefore, pi is not a solution. So it looks like the only two solutions to our problem are going to be pi over 2 and 3 pi over 2. And the main reason we needed to check our answers here, other than the fact that it's a good idea to do that anyway, is because in the original problem, the cotangent is actually undefined in a few places. And so it's a good idea to check the answers that you get and make sure that they work in your original problem. Example 8, solve the equation on the interval from 0 to 2 pi, cosecant squared x minus 1 is equal to the cotangent. All right, this problem would be much easier to do if we had all the same trig functions in there. And because I have a cosecant squared, I can check out my Pythagorean identities. And I have a Pythagorean identity that tells me the cosecant squared of an angle is equal to 1 plus the cotangent squared of that angle. And so what I'm going to do is I am going to make that substitution. I'm going to take out this cosecant squared and I'm going to replace it with 1 plus the cotangent squared. This problem becomes 1 plus the cotangent squared of x minus 1 is equal to the cotangent of x. All right. And what I notice now is if I add my like terms, the 1's look like they're going to cancel out. So we're going to take those out. We now have the cotangent squared of x equal to the cotangent of x. Now be really careful here. Don't divide both sides by the cotangent, because if you do, you will lose some solutions. So you want to be sure you get this thing equal to 0 before you try and solve it. Let's subtract that cotangent over to the other side. That gives me the cotangent squared of x minus the cotangent over here on the left, and it's equal to 0 on the right. If we factor out a cotangent, we're pulling out the GCF, we'll have the cotangent of x times the cotangent of x minus 1. Using our zero product property, we'll have the cotangent of x is equal to 0, or the cotangent of x minus 1 is equal to 0. And if we add that 1 over to the other side, we'll have the cotangent of x equal to 1. Let's pull this up here. If the cotangent of x is equal to 0, then we can say that x is equal to the inverse cotangent of 0. And if the cotangent of x is equal to 1, then we can say that x is equal to the inverse cotangent of 1. Let's look at the unit circle. The cotangent is 0 whenever the cosine is 0. So we're looking for angles on the unit circle where the cosine is 0, and then the sine, or the y-coordinate, is anything else except for 0. That happens at pi over 2 and 3 pi over 2. Over here, we're looking for the cotangent to be positive 1, and on the unit circle, the cotangent is going to be the x-coordinate divided by the y-coordinate. That means x and y are the same, and that happens at pi over 4 and at 5 pi over 4. And we don't really need to check these because both of my problems have cotangents in there, and these are defined at the cotangent, and these are defined at the cotangent as well. So my solutions will be right here. We got pi over 4, pi over 2, 5 pi over 4, and 3 pi over 2. Example 9. Solve the equation on the interval from 0 to 2 pi. The sine of 3x plus the sine of x is equal to 0. Okay, for this problem, I am going to go back to the previous lesson, and I am going to use one of my sum to product formulas. And the sum to product formula I am going to use is the one that says the sum, the sine of an angle plus the sine of another angle is equal to 2 times the sine of the sum of the angles divided by 2 times the cosine of the difference of the angles divided by 2. So let's translate this down here into our problem. My angle 1 is going to be 3x. My angle 2 over here is going to be x. All right, that makes this become 2 times the sine of 3x plus x over 2 times the cosine of 3x minus x over 2, and then this is going to be equal to 0. All right, so we took and we translated this whole thing right here using this formula into what we have right down here. Let's simplify our angles just a little bit. We have 2 times the sine, 3x plus 1x, that's 4x, and 4x divided by 2 is going to give me 2x. Over here, 3x minus x, that's 2x, and 2x divided by 2 is going to give me 1x, or just plain old x. Now we have 2 times the sine of 2x times the cosine of x equal to 0. And now I'm going to back up to section 3, and I'm going to use my double angle formula because I have a double angle right here, and the sine for a double angle formula was 2 times the sine of my angle times the cosine of my angle. I'm going to take just this piece right here, and I'm going to convert it using my formula. This is going to become 2 times the sine of x times the cosine of x. And then I'm going to bring this 2 down. So we have 2 times the sine of x times the cosine of x. And I'm going to bring this cosine down. There we go. Now we're equal to 0. Now, let's clean this up just a little bit by multiplying. So let's see, 2 times 2, that's going to give me 4. Then we have a sine of x. And then the cosine of x times the cosine of x is going to give me the cosine squared of x. And this is equal to 0. And I don't really need this 4 right here, so let's just divide it out on both sides. And I'm left with the sine of x times the cosine squared of x equal to 0. Now I can use my zero product property, where the sine of x is going to be equal to 0, or the cosine squared of x is going to be equal to 0. Let's bring this up here. The cosine squared x, let's see, we'll need to square root both sides here. And of course the radical and the square will cancel. We're going to be left with the cosine of x equal to 0. If the sine of x is equal to 0, then x is going to be equal to the inverse sine of 0. Or if the cosine of x is 0, x is going to be equal to the inverse cosine of 0. And now we get to our unit circle, and the places where the sign is 0 on the unit circle, that happens at 0 and at pi. And then over here, the inverse cosine of 0, so the places on the unit circle where the cosine is 0, that happens at pi over 2 and at 3 pi over 2. And we don't really need to check our answers here because both the sine and the cosine are defined at all of these angles here. So these are actually going to be my solutions. Example 10, solve the equation on the interval from 0 to 2 pi. The tangent of x plus 1 is equal to the secant of x. Okay. Sometimes it turns out that you won't be able to manipulate the equation or do any kinds of substitutions and come up with anything that you can do something with. For example, I can turn the tangent into the sine over the cosine, and then I can turn the secant into 1 over the cosine. And if I wanted to, I can multiply both sides by the cosine so I can get rid of the fractions. But that's going to leave me with the sine of x plus the cosine of x equal to 1. And this is not really helpful for me as far as trying to solve this equation, because what I would really like to do is have it equal to 0 so I can use my zero product property. So if you run into a situation like this, another option that you have is to raise both sides of your equation to the second power. So we can square both sides. And that's what I'm going to do here. All right, let's look at what that's going to look like. We're going to take the tangent plus 1 and raise it to the second power. And then we're going to take secant and raise it to the second power. On the left, this is going to give me tangent x plus 1 times tangent x plus 1. And on the other side, we have secant squared of x. All right, let's distribute here, or FOIL. The tangent times the tangent is going to give me a tangent squared. The tangent times 1 is going to give me plus a tangent here. 1 times a tangent is going to give me a positive tangent here. And then 1 times 1 is going to give me a positive 1 here. We have a secant square of x. I'm going to add like terms over here. We have tangent squared of x plus 2 of these tangent x's plus 1 equal to the secant squared. And since I have all tangents over here on this side, I'm going to see if I can put tangents over here where the secant is located. Now if I look at my Pythagorean identities, I know that 1 plus the tangent squared is equal to the secant squared. And so I am going to substitute. I'm going to take out the secant squared and put 1 plus the tangent squared in its place. Over here we have tangent square of x plus 2 tangent x, oops, got the t there, plus 1. we get all our terms on one side, when I subtract the 1 here, they're going to end up canceling out. And when I subtract this tan squared over here, they're going to end up canceling out. And so all that's going to be left is this 2 tangent of x. And on the other side, we have 0. I don't really need this 2 here, so I'm going to divide it over to the other side. That leaves you with the tangent of x equal to 0. And if the tangent of x is equal to 0, then it must be true that x is equal to the inverse tangent of 0. And now we can go take a look at our unit circle and find the place or places where the tangent is equal to 0. That means the y-coordinate needs to be 0, and then the x can be anything else except for 0. And that happens at pi over 2 and 3 pi over 2. Wait, no, that's not right. There we go. Try that again. That gives me the angles 0 and pi. Now, because our original problem right here had some trig functions that are undefined in places, we do need to check our answers. And we're going to check them in the original problem. So we need to know, is the tangent of 0 plus 1 the same thing as the secant of 0? All right, at 0, the tangent is 0. At 0, the secant, which is 1 over the cosine, so this would be 1 over 1. 0 plus 1 is 1. 1 divided by 1 is 1. 0 is a solution. Now we're going to check pi. We want to know if the tangent of pi plus 1 is equal to the secant of pi. The tangent at pi, this is going to be 0 over negative 1, so that's 0, plus 1. The secant at pi, this is going to be 1 divided by negative 1, so that's going to give me negative 1. 0 plus 1 is 1. On the other side, we have negative 1. These are not the same. Pi is not a solution. And the only solution to this problem is going to be 0. This is example 11. Solve the equation on the interval from 0 to 2 pi. Give the exact solutions in radians and give approximations in degrees rounded to 1 decimal place. Part A, the cosine of x is equal to 0.6. All right, let's see. We want to figure out if the cosine of x is equal to 0.6, that means that x must be equal to the inverse cosine of 0.6. Now, if we were to put that in the calculator, this would return to me a quadrant 1 answer. So we're finished with that one. We don't actually have to put it in the calculator because it's going to give me an approximation. So this is an exact answer. Now we have to be a little bit clever here because the cosine is positive in quadrant 1 and in quadrant 4. This is the one that we know. The angle right here is 0.6. In quadrant 4, the reference angle down here would also be 0.6. The calculator would give us the, oh, hang on, that's not right. We don't know what the reference angle is. Sorry. But whatever the reference angle is, and I'm just going to mark it as theta. Whatever the reference angle is here, we're going to have the same reference angle right here, only it will be negative because the calculator would give us the negative degrees or the negative radians. So how do we get from here all the way around here to the coterminal angle? Well, if we knew this angle, we would subtract it from 2 pi. But since we don't know this angle, we're going to have to subtract the whole thing from 2 pi. In other words, we'll do 2 pi minus all of this back here, my quadrant 1 angle, which is the inverse cosine of 0.6. Okay, those are my exact answers for the cosine of 0.6, and these are in radians. If I want to figure out the approximate for the degrees, then I need to check my calculator and make sure that my calculator is set to degrees. And then we will do second cosine, 0.6. All right, let's see, my calculator is in radians, so now it's set to degrees. And then we're going to do the second cosine, 0.6. This is giving me 53.1 degrees. And then over here, we need our quadrant 4 angle. That's going to be 360 minus 53.1. And that's going to give me 306.9. So my other angle over here, 306.9. These are degrees. All right, so here's part A. Let's change color so we can do part B. Part B, we have the tangent equal to -5. Well, if the tangent of x is equal to -5, that means that x must be the inverse tangent of -5. Now, the inverse tangent is defined in quadrants 1 and 4. This angle right here is going to be our quadrant 4 angle. But remember, the calculator is going to give me the negative angle there for the reference angle. We're going to know this one right here is going to be negative something. So how am I going to get from here all the way around so that I have the actual coterminal angle that's positive because it's between 0 and 2 pi? Well, that means we're going to have to do 2 pi minus the inverse tangent of -5. And this will be equal to x. This is our exact answer. And this is going to be in quadrant 4. How are we going to get the other tangent? Well, the tangent is negative also up here in quadrant 2. So now we want to get this angle that goes from here to here. Well, remember, if we know this angle right here, we also know that one right there. And so because the calculator is going to give me a negative angle for right here, I don't quite want to go all the way to, well, I'll go all the way to pi, but then I need to back up some. And so my other angle, which is going to be in quadrant 2, is going to be pi minus, well, actually we'll need to do plus here, the inverse tangent of -5. And that's going to put me up in quadrant 2, because remember, this thing right here is going to be a negative number. And that's going to back me up into quadrant 2. So here are my exact answers. Then to get to my degree answers, I'm just going to put a D here. We'll look in the calculator. Second tangent, -5. This gives me -78.7. But remember, in the calculator, we want to add 360 to this so that we have a positive angle. That gives me 281.3. This is quadrant 4. And then the other one, this is our quadrant 4 angle right here. And then I need to figure out my quadrant 2 angle. Remember, we said we were just going to add pi to whatever that angle was. Well, since we're in degrees, we're going to add 180 plus that negative 78.7. And my other angle is going to be 101.3. And this is going to be my quadrant 2 angle right here. Example 12. Use the graphing utility to solve the equation. The cosine of 3x is equal to 0.6x. Round the solutions to 4 decimal places. Okay. What we're going to do, since we're going to be using a graphing utility this time, or a graphing calculator, I'm actually going to be using Desmos, and I'll pull that up in just a second. All right. So the variable we're trying to solve for here is going to be x. And what I'm going to do is I'm going to separate this into 2 equations. One equation is going to be this side of the equation right here. The other one is going to be this side of my problem over here. And so what I'm going to graph is y is equal to the cosine of 3x, and y is equal to 0.6x. And then the intersection of these 2 graphs, or intersections, will be the solutions to my problem. So let's pull up Desmos and solve this problem here. Okay. Drag this back here. There we go. Now you can see the whole Alright, so now you can see the whole graph. Remember, on one side we were going to graph y is equal to the cosine of 3x, and then we were going to graph y is equal to 0.6 times x. Based on our picture over here, it looks like I have 3 solutions. There's one right here at negative 1.279 and negative 0.767. There's one right here at negative 0.659 and negative 0.395. And there's one right here at 0.435 and 0.261. Now remember, if we go back to the problem, we are in fact solving for x. So that means I actually want to have the x coordinates for all these points as the solution to my problem. That means x is going to be negative 1.279. Let's grab a pen here. Or x can be equal to negative 0.659. Or x can be equal to 0.435. And these are the solutions to my equation up here. Now, I didn't round them to 4 decimal places because Desmos back here only rounded things to 3 decimal places. So we have our angles, and these are listed in radians. And we can change that to degrees by multiplying each one of them by pi over 180.